So I think I'll make a start, if I may. Thank you all for coming to this talk. You've all had, I expect, quite a hot and steamy day out in the city, so thank you for coming. For those who didn't come to my first lecture, my name is Michael Benton. I'm at the University of Bristol. I'm a paleontologist. And I chose this title, in a way it's compared to some of the topics you've had, like the meaning of evolution and the origin of the Earth, the origin of the universe. This may seem a very narrow topic, but I thought I should choose something perhaps related to the areas we're passing today and tomorrow in particular. And by going into some minutiae, I can maybe show you some of the ways in which we work on dinosaurs and discover some interesting facts about them. So what I want to outline here is a little bit about the history of discovery of dinosaurs, the fact that we know them from many parts of the Earth, and then go into some detail, particularly on the dinosaurs from Romania, which are the best in Eastern Europe. So although we're visiting Turkey, Bulgaria, and the Ukraine, unfortunately there are almost no dinosaurs from those countries, so it would be a rather dull and slender lecture if I was to talk about those. But the story of the dinosaurs from Romania is quite extraordinary, because the person who began their study was a fascinating and bizarre kind of character who really puts we present-day scientists to shame. Amongst other things, he sought to become king of Albania. He failed, but the fact was he tried, and I don't think any living paleontologist has done anything like that. And indeed, the dinosaurs from Romania that I'm going to introduce you to are not the normal monster dinosaurs that you think about. They are dwarf dinosaurs. So we're going to explore what that might mean in terms of geography, the way islands affect evolution, and how on earth can you get dwarf dinosaurs. Indeed, how can I say that they're dwarf dinosaurs? So we'll explore that. Now, maybe this is a bit of a shock for you. This will wake you up. The first dinosaur ever named was called Scrotum, and that ought to be a name that we use, zoologically speaking. But paleontologists have been a timorous bunch, and so the name has been somewhat forgotten. But the history here is that the first published recognizable illustration of a dinosaur dates then from 1677 in this wonderful book by Robert Plott, who was a professor at the University of Oxford. And as was the way in those days, so many hundreds of years ago, the different branches of science had not been separated. So although he was called Professor of Chemistry, he also interested himself in all kinds of aspects of natural history. So his book, The Natural History of Oxfordshire, of which I have a copy, is full of these wonderful plates which illustrate natural wonders, which are objects, strangely shaped stones, and other things that he's collected and other people have brought to him. And this plate here, you can read at the top, this is plate 8, contains a variety of strange objects. And these were described tentatively, the one at the top left, as possibly a fossilized heart. It's just a piece of flint, and various other things, some of which are fossils, many of which are just curiously shaped stones. But it included this object here. And he correctly reasoned, and it's a fascinating book to read for this, if you want to see how an intelligent person with no background knowledge, because there was no background knowledge at that time. The word dinosaur had not been invented. How do you reason your way through in identifying something such as this? And he pointed out, for example, that the top was broken and it had a cavity in the center, and that it looked exactly like a cut-through mutton bone or ox bone. So he clearly compared it with what he'd seen at the butcher's. And then he looked at the texture of the bone and the hollow in the middle and said, this looks like bone. This really is bone from some huge animal buried in the rock. And even the word fossil was not used at that time quite the way we use it. He uses the word fossil, as other people did then, just to mean anything that is dug up out of the ground. That's the literal meaning. So fossils then included what we would call fossils, as well as these odd bits and pieces of flints and rocks, and stone arrowheads and even potatoes were all called fossils because they were dug out of the ground. But he then went on to say, if it's a bone, what bone is it? And he knew enough about the anatomy of cows and humans and other animals to be able to say, this is the lower end of the thigh bone, so the bottom end at the knee. But it was so huge, there isn't a measurement on that, but the thing is this sort of size. It's about a foot wide. So it's really huge. And he said it's bigger than the knee bone of an elephant. He'd seen an elephant in a travelling menagerie in Oxford. Although he'd not seen a skeleton, he could work out from the size of the knee. So he went through, and finally he argued that it came from a giant man or woman. So he was being very proper and politically correct. And his evidence was referring to the Bible, where the phrase occurs, and there were giants in those days. So it's vaguely human-looking. And the name then was given to it. He didn't name it, of course. Plott didn't name it, but this person called Brooks named it in 1763 as Scrotum Humanum. And I'm afraid I haven't seen Brooks's original book, so I don't know why he chose to name the thing. I think we can guess why he called it that. And I regret to say it is, for those of you who know about biological nomenclature, the key date is 1758 for animals. That is the Linnaeus 10th edition. So this is a formally correct zoological name. And now we would have to use it, but up until recently there was this term nomen oblitum. If a name is not used, if it is forgotten, then you can declare that this is a name we don't use. We now know that this is the lower end of the femur of Megalosaurus, which is a typical Middle Jurassic dinosaur from near Oxford. There's the first dinosaur. So I'll hop through a little bit more promptly now. The first, although that was named, it isn't treated, regrettably, as the first named dinosaur. Iguanodon is, and the story of this some of you will be familiar with. The first 3 or 4 dinosaurs to be named in the world all came from England. It just was chance that that was where people who were interested in such things happened to be working at the time. Gideon Mantell named one of the first. The first, in fact, to be named was by William Buckland. He named Megalosaurus in 1824. Mantell named Iguanodon in 1825. That was number 2. And Hylaeosaurus in 1833. That was number 3. And so it went on with furthers named from the UK. I'll stop for a moment. The story of Gideon Mantell is interesting because he was not a wealthy person. He worked as a country physician, collected bones and wrote books about them, and indeed wrote popular books about dinosaurs and the history of the Earth. But this became even more pointed in the most remarkable story in the whole of the history of science that I've ever come across. His enemy curated part of his skeleton. Think about it. His enemy curated part of his enemy's skeleton. So Mantell, I've mentioned, and Owen is the generally regarded as Mr. Nasty, which is probably partly fair, partly unfair. Owen also had to work for a living, but he made his way in society much faster and much more successfully than Mantell. He moved to London and became a professor at a very young age. And it was in charge of the museum of the Royal College of Surgeons in London, sadly largely lost in the Second World War. But he was a society figure, tutor to Queen Victoria's children, but he was a brilliant scientist, and almost every biologist will know his name. He was particularly important for his work on the anatomy of vertebrates, living and extinct. Here he is with the skeleton of a moa, one of the giant recently extinct birds from New Zealand. But he squabbled with Mantell. They were working on dinosaurs at about the same time. And they debated and bickered in print in a very pointed way that scientists wouldn't get away with today. Because all the scientific journals are monitored by lawyers who would prevent you from saying the sort of things they used to be able to say, like Professor X knows less than a schoolboy about whatever the subject happens to be. So in the end, poor old Mantell had suffered curvature, scoliosis of the backbone for many years. It said he fell out of a carriage, and for the last 10 years of his life, his backbone was kind of crunching up and binding and fusing. And so when he died, when Mantell died in 1852, somehow his backbone became part of the collection of the Royal College of Surgeons as an example of this fusion of the bones. So Owen curated his enemy's backbone. An extraordinary thought. And that was discovered, if some of you are interested in this, is a wonderful book by Deborah Cadbury on the early history of the dinosaur collectors. This was written a few years ago. The story then moves out of Europe, and of course dinosaurs continue to be collected in Europe, and we'll look at the Romanian ones shortly. But I wanted to just put this into the context of what you will also know is known about the dinosaurs from North America and how this fits into the world picture. So the first fossil dinosaurs from North America were identified as early as 1807, and indeed through the 1820s and 30s a number of books were written by Edward Hitchcock, who was a professor, I think, at Amherst College, and he identified these as genuinely footprints of some giant extinct creatures, but as birds. And now we know that these Triassic age footprints from New England are indeed footprints of some of the earliest dinosaurs. But the most significant early contributor to our knowledge of North American dinosaurs was Joseph Leidy, who was a professor at the Academy of Sciences in Philadelphia. And here's a picture of him with one of the bones he described. The first dinosaur specimens were not that impressive. They were from New Jersey. They were isolated bits and pieces. But he did have delivered to him a relatively complete skeleton of a hadrosaur, a duck-billed dinosaur, which he described in the 1860s. Most famously, though, and what really got North American dinosaurs on the map, were what have been called the bone wars of the late 1800s. Okay, very good. And thank you for not all rushing off to the casino and all these other attractions. I'll try and keep you amused and entertained. So the Bone Wars, moving on swiftly. In the late 19th century, two protagonists, you'll all be aware of this, I'm sure, Cope and Marsh. Cope was unbelievably active in his lifetime. He wrote, I don't know, 1,500 scientific papers. He named 1,000 new species. I don't think anybody else has come close, probably just as well. He worked on modern fishes and reptiles. He worked on extinct dinosaurs, as we'll hear, and mammals and all kinds of other things. And he was also very interested in evolution, and amongst other things, we refer to one of the many rules or principles of evolution of organisms as Cope's rule, which is a propensity of organisms to get bigger through time. On the other side was Othniel Charles Marsh, who was professor at Yale, and he likewise was very active in acquiring specimens and worked on a great variety of fossils. At first, it's said the two were reasonably amicable. They worked together. They met a few times. But from the 1870s onwards, their friendship disappeared. They became sworn enemies. And they were both running a kind of empire or business, more or less, to discover and name new dinosaurs. And the way it worked was that they had these raggle-taggle cowboy field crews who worked out in the Midwest. Particularly, these were railway builders, so as the railroad was built across the land, they were cutting across the Morrison Formation in the Jurassic and other geological units that are highly rich in dinosaur bones. They encountered bones. They reported back to these professors in the East, who would pay them dollars for their services. So the bones were being torn out of the ground, often with great speed, and it's reported at times either Cope or Marsh would be hiring whole trains to bring back tens of tons of bones in packing cases, and they would open these cases in Philadelphia and New Haven respectively, and before the things were hardly out of the rock, they would be writing the papers, and each had a pet journal where they could publish within 2 or 3 days. So to modern scientists who think we have fast publication, they really did it. But they had no peer review. That's the thing that we always find extremely annoying. And maybe the solution is we should all have our own journals, and then we don't have to worry about critical comments. And so this has been the subject of numerous books. I don't know where I got this Bone Sharps, Cowboys, and Thunder Lizards from, but and the wonderful Mark Twain quote, "There is something fascinating about science. One gets such wholesale returns of conjecture out of such a trifling investment of fact." And I think he was writing at the time of and commenting upon this rather poor illustration of how science can be done. They achieved a huge amount between them, but of course they could have achieved so much more if they'd worked together. But there we are. That's how these things go. By 1900, then, both Cope and Marsh were dead. That was the end of the great bone bonanza, but that was the time during which all the favorite North American dinosaurs were found. And it continued, of course, into the beginning of the 20th century, and further museums, the American Museum and others, filled up with dinosaurs after that time, but working in the same localities that Cope and Marsh had exploited. Meanwhile, people were looking for dinosaurs in other parts of the world, and this is where I introduced Baron Franz von Nopscha. He's clearly this interesting character that I referred to at the start. He was born at a time when the geography of Europe was very different from what it is today. So although he was born at this location called Hatzeg, which is now located in southwest Romania, at that time it was more part of Hungary, and it was part of the great Austro-Hungarian Empire, which in fact included Austria and Hungary, but also great chunks of Eastern Europe, and indeed bits of Italy, and all the Serb countries and everything else were gobbled up in the Austro-Hungarian Empire. So it wasn't a surprise then that he would be able to speak, as well as Hungarian, German, and numerous other languages, that he went to study at the University of Vienna, because that was the capital of this great empire. He belonged to a minor noble family, as you can tell from his name, which I won't attempt to read out. And he got set on the track of paleontology just by a chance, that his sister found some dinosaur bones on the family estates in 1895. And here is the family house, which you can still see today. I've visited there, and part of my reason for talking about this is I've had the privilege of working in Romania with Romanian paleontologists for a number of years. And in fact, the main group I'm working with are in the Department of Geology at the University of Bucharest. And when I first visited there in 1993, they showed me the bullet holes on their building that had been caused, I think, 2 or 3 years earlier when they threw down Nicolae Ceausescu. So exciting times, and we have to remember that these countries have had exciting times really quite recently too. So here is the Nopcsa family estate. He took these bones his sister had found. He's just a young man at the time, aged about 20. He's a student. He showed them to Edward Suess, who is a very famous geologist, and he told the young man, study them yourself, write a paper about them. So he did, and published his first scientific paper in 1899. And after that, then, Nopcsa continued in his field of dinosaur studies and published numerous papers in many languages, in English and German and French, and he became quite well known throughout Europe. But it was a rather impoverished noble family, as so many of these are. So he had to find a way to make a living. And he never really had a regular academic job, unfortunately. And so he tried various things. And when you see him in his various outfits as a warrior during these early years of the 20th century, I don't know who he's acting for in these different garments. But as I say, he puts us all to shame today. No scientist would do these sort of things. So he was an irregular soldier for all sides. I think it's now known as a fact that he spied for England and for the Austro-Hungarians during the First World War. After the war, Albania had no king. The royal family hadn't produced a son. So he very generously offered to step in and be the king. Why not? Regrettably, he didn't succeed. He was also a homosexual in a time when that was not terribly acceptable. And he traveled Europe on a motorcycle combination with sidecar with his secretary, and in the end, regrettably, at a youngish age, at about 50, he shot his secretary and shot himself and killed them both. Nonetheless, he'd had a remarkable career in science, and I won't read through all of this, but this is a summary of some of the things this man achieved. His name is not very well known, but he had a rather odd kind of life. He was never a professor in a university or any of the standard kinds of things. But he really achieved great things, which I'm going to develop further, particularly the third and fourth item. Because not only did he discover and name dinosaurs from his home country, but he also thought about them and wondered, how did they live? Why did they look the way they did? And he wrote about standard sort of topics: what did they eat, how did they move, those sort of things. But he also was the first to talk about sexual dimorphism. That is the phenomenon of males and females looking different, which we're very familiar with in modern birds, where very often the male is quite colorful and the female may not be. But you can actually detect this often in the fossils, because the skeletons may be of different proportions. He was also very interested in the origin of birds, and he wrote about the origin of flight, and also taphonomy, which some of you may know is the study of preservation of fossils. And these are all themes that we work on now, but back in the early 1900s they were not so commonly done. So here is Eastern Europe. We're currently in Turkey. Here's the Bosphorus, and we'll be going into the Black Sea, and Varna is here, and Odessa is, where is it, somewhere in Crimea. So here are the countries of Eastern Europe. Romania is here. There are various dinosaur deposits in northeast Romania. I've worked up there. And Hatzeg is down in the southwest of Romania here, and I've worked in that area also. And there really are very few dinosaurs from these other countries of Eastern Europe, unfortunately. But the Hatzeg dinosaurs are particularly interesting, so I think they make a nice story to develop a little bit further. And there is still a great deal to find. So just a matter of last year, this remarkable new, small, rather fearsome dinosaur was described from Romania. So there are still new beasts coming out. And I think there's going to be a lot more, actually, as the political and economic situation improves in these countries. There will be more opportunity for native scientists to go out and collect. and for more collaborations. I must say, when we went in '93, and they said, oh yes, here's the bullet holes, and I saw them being formed, you think, right, okay, should I be here or not? Just a reminder of Ceausescu. If you've been to Bucharest, one of the most startling buildings is this enormous monstrosity that he built. And as far as I'm aware, it's still not occupied. So Ceausescu had very grandiose ideas, and he designed this and wanted it to be a kind of people's palace. It was going to be the biggest building in Europe. And when I visited in the 90s, this was not occupied. It was just standing there. Why there's a Toyota sign in front of it, I can't imagine. Anyway. So Hatzeg, this is what the scenery looks like. It's on the edge of the Carpathian Mountains. It's an area of Romania that is called Transylvania. If you've heard of Dracula and Vlad the Impaler, this is where they come from. Nothing to do with Notcha, though, I don't think. But geologically, this area is really quite important because there are a great deal of rocks of Upper Cretaceous age. They occupy large areas of these mountains. And in fact, because of the geology and the dinosaur finds, which I'm going to describe shortly, it's a UNESCO geopark. Here's an example of, here's a field trip we were on, and many students and others going up and down the rocks. You can see the bedding of the rocks. These are sandstones and mudstones, and at different levels there are rich remains of bones. These are the kinds of bones after they've been cleaned up. That's the sort of quality of preservation, just to give you an example. But one of the standard field techniques that we often use is you don't just wander around picking up bones, nor, of course, if you remember Jurassic Park. Let me let you in on a secret here. You may remember near the beginning of Jurassic Park, they had a wonderful machine that they seemed to be able to place over the rock, and it sort of showed like an X-ray, a dinosaur in the rock. Now, I don't know whether you believe that there is such a machine in existence, but let me tell you, there is no such machine, so you have to go poking around and digging. And the second thing is, I seem to remember having located the dinosaur. You look with this super spy scope, and there it is. You just take a little brush, and there's the skeleton. Well, I think you know it's not like that. It's hard work. And collecting the big bones, you tend to prospect. Some of you may have done this in the American Midwest. It's the same here. The exposure is not great because it's quite lush farmland, but you look for isolated flakes of bone by the riverbanks, let's say, and you simply follow them up the erosion gullies and hope to find complete bones. Also, we're very interested in small bones, because of course they may give evidence of birds and mammals and lizards and other interesting creatures of that kind. And so the initial stages are simply you take buckets of sediment down to the river and you wash them through sieves, and you can make a very simple sieve with a kind of plastic milk thing like that with some mesh. And you just sieve away the clay and you take the concentrated stuff back to the lab and pick over it. So here is Hatzeg on the Cretaceous world. The continents are different from today. I'll talk a little more about that in a moment. And you've already heard a little about plate tectonics from Dr. Weissession, so this will link with some of what he was saying in the Santorini lecture. So Hatzeg is nearer the equator at that time than it is today, and sea levels then were much higher than they are today. And that's why the continents seem smaller, and there are wider areas of continental shelf. And this is particularly important for the Hatzeg story, because whereas Europe is a continent now, in the Upper Cretaceous it was an archipelago of islands, and this is a key fact that we need to know. Reconstructing the scene gives you a picture something like what's on the right. This is based on an analysis of the plant fossils and other kinds of fossils preserved with the dinosaurs. And they attest to lush vegetation, semi-tropical climate, and rather warmer and certainly more lush and humid than it is today. So I think most of you will be very familiar with the story of continental drift and then the mechanism of plate tectonics as an explanation for how it happened. But just to remind you that the initial evidence was rather obvious in certain ways. Many people noted in Victorian times how the continents seem to fit together, something like this, that South America would fit into the sort of west coast of Africa like that. And of course it was Alfred Wegener, who I think Dr. Weissession mentioned, who brought all of this information together and added some geological information. He noticed, for example, that there are coal deposits in Brazil on the coast which match coal deposits of the same age, mid-Permian, in West Africa. So not only do the continents fit together snugly, you can trace the rocks across from one continent to the next. And you wouldn't expect to be able to do that in detail, because obviously with the passage of hundreds of millions of years, you lose a lot of the detail. But nonetheless, it was quite remarkable, some of the sedimentary basins track across. Also, he noticed that across southern Africa and all of these continents, including India, there was evidence for a major glacial episode, a time when there was movement of ice across what are now land masses. And that evidence was in the form of great scratches or striations on the older rocks. And we're familiar with those, of course, in Canada and northern Europe. You can see them there. In many places, the rock has been skimmed off and it still hasn't covered up. And you can see these striations which mark the direction of movement of the ice. And so you probably can't quite see this because of the scale and the fact the boat is jumping up and down. In southern Africa, these arrows are pointing in the direction of movement of the ice. So they're all pointing outwards, and there's a sort of focus in the middle here, and they're pointing up and down, and then into South America they're pointing west. There's nothing known really from Antarctica because it's covered in ice, so you can't really see that. In Australia they're pointing from the south to the north, and in India they're pointing north. And so people were debating this around 1900. How could we have movement of ice across India? Because remember, India today is north of the equator. So somehow you have to explain ice sheets going from a source in the middle of southern Africa and somehow going across the Indian Ocean, across the equator, across India. Ludicrous. But of course, if you push the continents together in the familiar jigsaw pattern of Gondwana, then these moving ice directions all point outwards from a center point in Africa. And we know that, in fact, that was more or less the South Pole at that time in the Permian, about 300 million years ago. This very poor illustration, I'm sorry this didn't reproduce very well. I got some internet on Santorini, and I was grabbing images off the internet in a cafe, and it drove me completely mad because it kept cutting out, and I couldn't get what I wanted. Anyway, we had a great view while I was cursing at the computer. Nonetheless, there are a number of, all I can say is this is the standard Gondwana arrangement, and as well as the geological evidence, there are, of course, there's evidence from distribution of plants and reptiles and other creatures that you can find exactly located on these different southern continents. And you'd have to suggest that these creatures were somehow able to cross the South Atlantic, to cross the Indian Ocean, these massive southern oceans, which would be unlikely for these terrestrial plants and animals. Whereas if you push the continents together, it all makes sense, biogeographically speaking. You're also familiar with this sequence I showed in the previous lecture, and this ties with some things from Dr. Weissession's lecture. And to remind you that although this starts in the Permian, the time of Pangaea, there were continental movements before that, separate continents, they came together, and these movements since. So continental movement is one thing, and of course the distribution of dinosaurs depends upon the positions of continents. So for example, in the Jurassic, it's no surprise, or should be no surprise, that the dinosaurs of the Morrison Formation here in North America are very similar to dinosaurs from Tendaguru in Tanzania. Today, that would be very hard to explain, because they would have to get across the ocean. You're talking about very different climate zones and so on. In the Jurassic, they could have simply walked across Spain and Europe into North America and back and forward. So throughout the world, dinosaur faunas were rather similar because the continents were more or less joined together. But it's very important, and people often forget this, that in trying to understand distributions and how the Earth may have affected evolution, particularly evolution of terrestrial life, that we also have to think about sea level change. It's a combination of these two that then gives us the correct understanding of how organisms moved and how the breakup and movement of continents, combined with changes in sea level, will affect the relationships of groups in different parts of the world. Now, maybe the detail here isn't very good. I'm sorry about that. This is a sea level curve through the Phanerozoic. The present day is at the top. The red line is present day sea level. And for some reason, they've plotted it with high sea level on the left and low sea level on the right, so that you can see at first that through much of the Phanerozoic, at least, sea level has been higher than it is today, and sometimes considerably higher. So in the late Cretaceous, which is here, it's 100 meters high or more. And that's quite something to think about, because, of course, in all the discussions about global warming and sea level change that's happening now, and maybe in the next 100 years, people are worrying about a movement of maybe 5 meters change. And we know that a rise in sea level of 5 meters would wipe out cities like London, New York, Tokyo, many more. But if we're thinking about what could happen, in the past then sea levels have been 100 meters higher or more. Now let's think, how could that be before we move on to, it's easy just to say that, but I think it's important that we try to understand why that would be. So I think we know that sea level today is quite low. What's the main reason that that would be? Yes, ice. If you lock up a lot of water as ice, you remove it from the ocean. So whenever there is an ice age, sea level will be low. So there's an ice age today, or at least there's ice at the poles, and there has been a lot of ice in the last 10 million years, hence these rather low sea levels. And then in the past, it looks as if there's lows here at the beginning of the Jurassic, and here particularly at the beginning of the Permian. That is the southern polar ice age, which removed a lot of water from the system. There are other reasons why sea level would be high in the Cretaceous, and I've given a hint at them there. First of all, there was no ice, so then it's no surprise that sea levels are already high for that reason. But there are additional reasons why sea level was high in the mid-Cretaceous. One of them is connected with the fact that there was enhanced mid-ocean ridge activity. So this means that the mid-ocean ridges were spewing out basalt lava faster than they normally do. Now, why would that make sea level rise, do you think? If you've got an enhanced volcanic activity, enhanced mid-ocean ridge activity. Can you think why that? Yeah. Okay, probably would do that. I'm not sure why that would raise sea level. Oh, yeah. Okay, so there's no ice and sea level is high anyway. And the mid-ocean ridge activity actually raises the floor of the ocean. So it's just like pushing up the bottom of your bathtub and the water flows over the continents. So we have to think of, obviously, as you heard in Dr. Weissession's talk, the driver of plate tectonics are the convection cells, and they come together, and the magma rises in the mid-ocean ridges up the middle of the Atlantic, and in various lines through the Pacific and the Indian Ocean. And as at certain times in the history of the Earth, that magmatic activity has increased. The convection cells go faster and faster, driving up the center of the ocean. And that raises the whole center and can reduce the volume of the center of the ocean and push the water out sideways. In addition to which is simply that without the ice caps, climates were warmer as a whole, and the warmth will make the water expand. So there are three reasons for high sea level in the Cretaceous. The absence of ice, that's the easiest. Enhanced mid-ocean ridge activity, that pushes up the floor of the ocean. And thirdly, the thermal expansion of water, which we're also concerned about at the present time. So all those reasons gave high sea level in the Upper Cretaceous. And so Eastern Europe looks like, well, the whole of Europe looks like this. So it's mainly ocean, which may come as a surprise. Some of you may be familiar, though, with the White Cliffs of Dover. And so here's the UK, this is Ireland, and this is Britain, and here's Dover. And so with sea level 100 meters higher, most of the UK, most of France are completely swamped, and marine sediments are being deposited, including chalk. And importantly for dinosaurs, which are known in Europe at this time, let me get myself straight. Here's the Iberian Plate, so this is Portugal and Spain over here. This is the south of France here, so you can see there are separate islands. And this is Switzerland, so I guess Italy is somewhere in here. Germany, Poland, and so Romania is somewhere in here. And this mess of continent boundaries and plates rotated in different ways is what the Turkish area looked like at the time. So you may recall in Dr. Weissession's talk about Santorini, he showed you some tectonic maps of Eastern Europe and the Black Sea area, and you're well aware, of course, that this whole area is tectonically very active. So in making these reconstructions back into the past, we not only have to think about the big picture of plate movements that we're all familiar with, we also have to think about these more regional scale phenomena, such as the different faults and so on that are operating, and the way Turkey moves. He gave a very graphic image of Turkey kind of squeezing out between the African and Asiatic plates. But then you have to pick that back. You have to go back and try to work out what it might have looked like then. And then you lay on top of that increased sea level, giving you really lots of small islands, with dinosaurs located on some of them. And it wasn't only Europe that was affected. North America was split in two. You may have heard of the Western Interior Seaway, and with increased sea level, much of eastern Mexico and Texas, and then all the way up through to Alberta and up to the North Pole, essentially. It was a wide open seaway, which divided North America in two, and the dinosaurs couldn't get across. So we got different dinosaurs on each side. And even this ridiculous cartoon of mine doesn't show up very well. Come on, Rex, you can do it. Jump, boy, jump. Hurry, Rex, hurry. So this is supposed to be continents splitting apart. They wouldn't move that fast, of course, so nobody would be abandoned quite like that. So this is the final point on the paleogeography. This is a different map, but more or less showing the same pattern, but just concentrating on what it looked like in Cretaceous times. It's a bit harder to understand it without the modern geography marked. But this is Spain here, this is Britain, and this is where Hatzeg was located, on that island there. And it seems then that these islands were not only existed, and dinosaurs were on them. How they got there is somewhat debated. Were they stuck as the sea levels rose, and they were just kind of plonked here and there? Sea levels rose and they hunched into smaller and smaller areas, or did they somehow get there in the way plants and animals get onto islands? And we've heard about that from Dr. Noor, that, as you know, this is an important area for us to study evolution, to try and look at islands where we can date their origins and look at patterns of how group organisms get there and how they evolve. So we don't know the answer to that. We do think, though, probably they were marooned rather than that they somehow struggled out there, because we can link them back to dinosaurs from other parts of the world, as we'll show in a minute. But as far as we know, these islands were isolated for at least 40 million years, so there was a lot of isolated evolution going on, and we can see the consequences. Let's look at the fauna. So there were all sorts of normal types of organisms that we would be familiar with, turtles and crocodiles, birds and mammals, all of which are very interesting. This is an important time to study these creatures, but I won't talk about them. I'll show you just this one giant pterosaur because it's big and people like big things. And this is Hatzeg opteryx, giant pterosaur. And finding such a creature on an island is no problem, of course, because it can fly. So it doesn't tell us anything particularly interesting about island evolution. In fact, it's very big, and fortunately, this is one of the things that certain paleontologists enjoy. There are no complete skeletons. Therefore, following Mark Twain's dictum, we can speculate freely. And people have estimated wingspans of 10 meters or more based upon rather isolated bits and pieces. I really don't want, though, to talk about this pterosaur because it doesn't tell us anything about body size. What is more important is to look at the dinosaurs. One first observation, and maybe this is something typical of islands, there are no large predators. This is one example. There are 2 or 3 theropod dinosaurs, flesh-eating dinosaurs, of which this is one. Elopteryx, this is a couple of reconstructions of it. it's only a metre or so in length, maybe 2 metres in length. So the fact is there are no large predators, and normally if there are big predatory dinosaurs, you at least find their isolated teeth. And I've shown you already people have searched quite intensively in this area, including sieving the sediments. So if there were some predatory dinosaur teeth from large animals, they would have found them. So let's just store that away and keep that in mind. There are predators. They themselves are not particularly large or small, and presumably Elopteryx is feeding on the mammals and lizards and other smaller creatures on the island. But when we look at the other dinosaurs, which normally would be very large in other parts of the world, this is where Nopcsa got his first surprise. Because he found amongst his early collection back in 1899 bones of what he later called Magyarosaurus, meaning the Hungarian dinosaur. And they were big enough, but when he compared them with other specimens of related dinosaurs from other parts of the world, he discovered they were unusually small. So the first assumption is, well, maybe it's a juvenile. And we'll look at how you could try to distinguish that. But a second point is, interestingly, Magyarosaurus had its nearest relatives in southern continents, as shown there, not particularly in other parts of Europe. A second dinosaur to be named was Struthiosaurus. This is an ankylosaur. And if you're unsure about the different groups of dinosaurs, can I refer you to the wonderful full-color wall chart that you were sent by Neil Bauman? You can unfold it in the privacy of your bedroom and locate the different dinosaur groups later. Struthiosaurus is an armored dinosaur called an ankylosaur, and Nopcsa noticed, and people have noted ever since, first of all, it seems unusually primitive. Here's another little fact to store away. First of all, no big predators. Secondly, some of the dinosaurs, maybe all of them, we'll see, seem unusually primitive. Because even Nopcsa noticed that the closest relatives of this thing included animals like Hylaeosaurus from the early Cretaceous of England, something like 40 million years older. So not only are there no large predators, some of the dinosaurs seem quite primitive. Here's another one, Telmatosaurus, which is a hadrosaur. It's a plant eater, two-legged. Normally these things would be maybe 8, 10, 12 meters in length. This one is 4 meters, so it's big enough, but still small compared to its relatives. And again, Nopcsa and others noticed it was rather primitive. It was more similar to dinosaurs from the Wealden of England, which is early Cretaceous, than to the late Cretaceous dinosaurs of North America and Mongolia, for example. And I think the final dinosaur I'm going to show you, and I'm sorry we've lost his head in the skeleton, is Zalmoxes, which was named quite recently. There are 2 species, again 3 meters and 4 meters long, big enough, but much smaller than their relatives, and equally rather primitive. The closest relatives are considerably older. So what do we make of all this? We have to then determine, are these dwarfs or juveniles? So here's Magyarosaurus at the bottom, the sauropod. Here is Zalmoxes at the top, the ornithopod. And compared to a human being, they're quite small. And lost in the image, I can't see it, unfortunately. There's a paler silhouette of a close relative, so I'm sorry you can't see that. The close relative of Zalmoxes is twice the length, and the close relative of Magyarosaurus is twice to 3 times the length. So how can we determine whether these are dwarfs or juveniles, and how can we then make sense of the primitiveness and the absence of predators and those sorts of things? Well, we did a study of this, and this was published last year. I was working with colleagues from Germany and North America, and we got access to the wonderful collections from Romania, including, for example, a set of bones of Magyarosaurus. These are the humerus bone, which is the upper bone of the arm, and they range in size from this one here, which is identified as probably a juvenile, through to these 2, D and E, which are referred to as probably adult. And what can we make of that? There's a certain amount of circumstantial evidence. You could say, well, this looks like a sort of growth series, and we don't really find anything bigger than this one at E, so presumably that's the adult. And it looks plausible. But it's not really strong enough evidence, because somebody could say, yes, but there's probably a bigger one that you just haven't found. And also, there are other ways as well. You can you can also look at other bones to detect whether there's fusion of sutures. So some of you will be familiar with the fact that as human beings grow up, the sutures in the skull fuse together. And so a baby has a fontanelle where the sutures are not fused, and as they get older, that covers over the bone and fuses and becomes firmer. And you can do the same with dinosaurs. You can look at their parts of their skeleton, and indeed it turns out the bigger ones have got fully fused bones. So there's two pieces of evidence. You might say, well, they're actually adults, and therefore they're dwarves, they're not juveniles. But it's still not quite strong enough. So what we did was to look at the bone histology. And this involves cutting the bone across and looking at it under the microscope, both in plain and so-called polarized light. So here are a couple of sections at A and C, and in the boxes are the areas that we look at in more detail on the right. So B and D are blown-up versions of these cross-sections of the bone. And I'm just trying to remember which is which. So the larger animal is here, and the smaller one is here. So what we found when we looked at these bones was that the larger animals showed considerable maturity of the development of the bone. Now, how do we know that? There are certain features within the bone of any animal, whether living or extinct, that can tell us something about their stage of development. Now, first of all, you might be surprised that we can do this with dinosaurs, but I can assure you that any dinosaur bone that you cut across will show you the same internal architectural detail that you can see in a modern bone. So you can get all that information about the structure, the way the areas of the bone are constructed, that there are certain patterns, layers, and so on within the bone as it grows. And as the animal gets bigger, the bones expand, and more bone is laid down on the outside and on the inside, if there's a sort of hollow center. But a second thing that happens in our bone, in mammal bone, and in the bone of birds, and the bone of dinosaurs, is called secondary remodeling. So what this is that as the animal gets older, the bone, of course, has blood vessels and nerves running through it, and you get these structures called secondary osteons, or Haversian systems, named after the anatomist, Havers, who noted them first. So in our bone, there is a regular structure that is the primary structure, and that's all you would see in the bone of a juvenile. But when you become an adult, your bones stabilize in size, but you're continually remodeling the bone, because, of course, bone has two main functions. One is as a support to hold the body up and attach muscles to. The second is as a store of minerals, and you store calcium and phosphorus in your bones. That's what bones are made of. And these blood vessels and other living tissues that run through the bone will pick up and remove calcium and phosphorus from the bones when it is needed for other purposes. And then when you're well fed and you don't need the calcium and phosphorus, it is deposited again around the blood vessel. Hence you get these circular structures, which first of all are eroded out by the blood vessel to take out the calcium and phosphorus, and then when food is available, they fill up again with concentric circles, filling inwards. So they're like the rings of a tree, but they don't grow out, they grow in, because the blood vessel is in the core of that structure. So a bit of a long-winded explanation, and I apologize to the medical people here because I've probably not quite got it right. But nonetheless, secondary bone remodeling, which is seen in human beings and mammals in general and in birds, is seen in dinosaurs. Now, the more juvenile bone has got relatively little secondary remodeling. There are two of these Haversian systems in that view. The older bone shown here is packed. It is or the reputedly older bone, it is completely remodeled, all these circular structures. So a long-winded explanation, but the point is you can get supplementary and really quite devastating evidence for maturity from the bone histology. Looking at a second species, we found the same thing as well, and you can even estimate the age of death by counting lines of arrested growth, as they're called. So maybe you can just about make out, the views are not, it's not so easy to see here. Maybe in this lower one you can just about make out that there are maybe 1, 2, 3, 4, 5 lines that cut across the primary structure. And so the bone in these dinosaurs is growing somewhat episodically. It shows some mammalian characters in the secondary remodeling, which suggests high metabolic rate, maybe what we would call warm-bloodedness. But secondly, it's showing a layering, or a kind of annual growth ring. It's a bit crude, but nonetheless seems to be true. And that's a characteristic today, typically of cold-blooded animals, like crocodiles and lizards. And they lay down rings of bone on the outside as the animal gets bigger, and they tend to correspond to times of rich food and good climatic conditions. So typically the summer. So you get rapid growth in the summer when food is abundant, and then you get a slowdown, which is marked then by the line, or line of arrested growth, as they're more technically called. So in this case, we can actually age the animals, we believe, and the upper one is 7 years old, the lower one is 11. You haven't got the entire section here, so that there should be more down here, and then you could count 11 lines. And the outside of the bone is here, and in many of these examples it shows the features of cessation of growth. There are particular features on the outside of the bone when growth stops expanding, and it lays down particular thick layers as a kind of protection or solidification of the external structure. So we were able to do those studies, and they were quite elaborate, but we felt we had to do them because otherwise people would criticize us and simply say, oh, they're all juveniles. So all of this grand story you're making up about dwarves means nothing at all. So secondly, we wanted to compare these, now we believe convincingly having shown that they are small adults, not normal-sized juveniles. What does this mean? Because this is leading us to an important conclusion about evolution that relates to what we know about islands. And again, I must apologize, snatching these images from our paper, they're not as good as they should be. We're comparing here Talmatosaurus with its relative Maiasaura, which I think is on your poster, a well-known dinosaur from Montana, which is normal size. It's about twice the length of Talmatosaurus. And then these lines are plotting the humerus length and width, and the femur length and width. So it's looking at the proportions of the main leg bone and the main arm bone, and they fall on pretty much a straight line, which is from juveniles or very small forms up to very big forms at the top. So all this was showing is that the pattern of growth, the sequence of growth in the proportions of each of these bones is very comparable between our Romanian dinosaurs and the normal kinds of dinosaurs which are closely related in other parts of the world. So this suggests that Talmatosaurus grows and grows and grows and grows and stops about here, whereas Maiasaura continues to grow up and up and up to here. So somehow the Romanian dinosaur has stopped growing, or at least relative to the normal relatives, it's a small adult. And there are various ways in which this could happen, but technically this is called a pedomorphic process, which means replicating a childlike appearance in the adult, a juvenile adult, and probably by the sub-process of progenesis, meaning early cessation of growth. And the evidence from these measurements tends to suggest that the animal just grows according to the normal pattern of its family, of its group, but for whatever evolutionary reasons, whatever those selective pressures are, it just stops growing at a certain point. Whereas in other parts of the world, it would keep going. It would not reach sexual maturity until it is up to this size. In Romania, they hit sexual maturity at half the size. So let's just save that up and see how we put all this together in a moment. I did mention earlier the primitiveness of these, and when Nopcsa did his studies, he could only report that as a general impression. And of course, often hunches and general impressions are right. But of course, you're aware of the fact that in the last 100 years, as scientists, we have to be much more precise, and we have to deal with evidence. It's not enough these days. You won't get your papers published if you just say, I've got an idea, I've got a hunch, I think this is what goes on. You'll be asked to provide numerical evidence. You must provide evidence. And so in this case, we also did a fairly detailed study of each of the Romanian dinosaurs. Here's Magyarosaurus, here is Zalmoxes as two examples, positioning them in an evolutionary tree, first of all, and secondly, trying to relate that to the geographic origin of the different groups. And this is quite an elaborate analysis, so I'll only show you these examples to show you what could be done. Now let me explain first of all this, this pattern of lines, some of you will be familiar with, can be called an evolutionary tree, is often called a cladogram. It doesn't have a time scale, although it can have a time scale. It is simply meant to be a geometric representation of relationships. These two are nearest relatives, then this is the next nearest relative, then Magyarosaurus is next, and then Trigonosaurus is next, and so it goes on. And you've seen these kinds of diagrams of human relationships, human, chimp, gorilla, that kind of thing. It's just a quick way of showing pattern of relationships. The data used to develop the tree could be morphological data, characters of the bones, which is what we have to use here, but equally it could be molecular sequence data, and I'm sure we'll hear more about that from Dr. Noor in due course. So any kind of data that gives you information about hypothetical ancestors and propinquity of relationship can be shown that way. But on top of that, the continent shapes, the cartoons, are meant to represent where each of these animals comes from. And first of all, notice Magyarosaurus with the European continent is sandwiched between a South American form and an African form. And this is an Asian form, and this is a Madagascar form. So it's a collection of Gondwanan dinosaurs, and there's this European thing sitting in the middle. So that's telling us, first of all, we're doing it on a proper phylogenetic tree, so we're reasonably clear about the relationships, and it's showing that it's quite primitive, because many of these are much older. So that's an additional demonstration of primitiveness. We call them relicts. So just to summarize, before we get onto the denouement, if you like, what this all means, or what other evidence we have to try and support it, it seems then very clear we have strong evidence that Hatzeg was an island, and it was an island for at least 40 million years, that perhaps dinosaurs were marooned on this because the whole world was dividing up into islands as sea levels rose, and therefore perhaps, for whatever reasons, these different dinosaurs didn't continue to evolve at the same rate or in the same way as their nearest relatives on the bigger continents like North America and Asia. And hence they become kind of living fossils of their day. And secondly, they're unusually small. I hope I've convinced you that we've been able to demonstrate that they are small adults and not just all juveniles, a sort of baby colony of dinosaurs. These truly are dinosaurs of different ages, and they're reproducing, and we've got a decent population of them. Now, of course, when we saw this, and indeed Nopsher was familiar with this, he immediately thought of these wonderful dwarf elephants from the Mediterranean islands. They were actually being discovered and collected and studied at the same time. So in the 1890s, there were papers being written. And again, I'm sorry, this hasn't reproduced terribly well. You can maybe make out an outline of an elephant in the background. And here's a human being. So here's a beautiful little elephant. And this is adult, and it's about 1 meter high. So this would make a decent sort of house pet. And that's a standard elephant from Sicily and Malta a few tens of thousands of years ago. And here's another one, a bit bigger, but still a dwarf. So you may have heard of the fact that on Malta and Sardinia and Sicily and some of the other Mediterranean islands, in the last 50, 60,000 years, there were dwarf elephants and dwarf hippos and dwarf deer, and there were giant dormice. So very weird things are happening on islands. The big things get small, and some of the small things get big. And I was trying to find it, but in my efforts in the cafe in Santorini, I just couldn't find this internet image of a giant mouse and a tiny elephant sort of facing up to each other, but it's a wonderful image. And of course this has been known for quite a long time, and people have had a number of explanations for what may be going on. Here's a skeleton of one of these little creatures with I think just a horse in the background. Could it be that on the island normal competitive pressures are removed and the animals can achieve some sort of size that they're more comfortable at rather than being forced into a niche that they're not happy with? Or could it be that there's expansion of the diets and other habits of the animals because there are simply fewer species? It is a fact that on islands there are generally many, many fewer species than elsewhere. Could it be resource limitation? This would also make sense in the case of the elephants and the dinosaurs. If you are big, you need a lot of food. You need a lot of area to get your food. We know that elephants walk enormous distances to find enough food. As areas dry up, they have to keep moving. So it may be, and this is probably the case for these Mediterranean elephants, and very likely for the dinosaurs. simply lack of food. You are better at surviving if you don't need a lot of food. And so the smaller individuals will be selected for. The fourth one is a little bit, seems to me a little bit mystical, but has been presented by evolutionary ecologists, that perhaps there's some kind of optimization of life history traits towards more R-selected modes, which I think what they're suggesting is that when land areas get smaller, when you move onto islands, it's better to be able to breed fast and to be able to try and repopulate, and that's an R-selected trait, ecologically speaking, breeding fast and not caring for the young. And getting smaller is part of that regime. But I think the niche expansion in the face of fewer species associated with resource limitation, I think those are the keys to this. And I don't think we have to choose one or the other. I think it's a mixture of various ones together. Here are the dwarf deer as well. Here's a standard-sized deer and a couple of dwarf deer examples. And I just love this idea. Wouldn't it be wonderful to visit Crete or Sardinia with pygmy elephant, pygmy hippo, pygmy deer, and these large rodents and shrews? You can just picture that. So I think then, to summarize what we've found in Romania, is that these dinosaurs then were a quarter size or smaller, because remember, and time is pressing, so I won't need to allow a few minutes for questions. Half the length means 1/8 the size, 1/8 the mass, because of course length is a linear measure, so it's a half times a half times a half to get mass. So they're 1/8 of the body mass, half the length, 1/8 of the body mass. And that then becomes quite a clear difference, because it's the body mass that determines how much you need to eat and things like that. They're clearly not juveniles, as I've shown. Very likely they became dwarves, all of them, maybe during those years of isolation, and probably all by the same process, just by limiting the time they take to grow up. It means they become adult at a younger age and at a smaller body size. And they are relicts or living fossils, and so they're fossil living fossils, which is quite remarkable. So I just want to wrap up with this slide here, and this is a taster for the next dinosaur lecture, the fourth one that I shall give. That dinosaur diversity was substantial, and yet we are still discovering many new kinds of dinosaurs, and that poster that you received from the Bright Horizons group then will give you some examples of this great diversity that are known. But more importantly, or as importantly, by using smart new research techniques of some of the kinds I've shown, and I'll talk about others in my next lecture, we can actually go a lot further than people maybe thought would be possible, and certainly than was possible in the past. And rather than just making a conjecture, which you have to do, that's your start, that's your hypothesis, you have to look at different angles of how can I actually test this. And here is a case where I think we have really good evidence from quite distant time, from quite deep time, of really a very fascinating evolutionary geographic question of the kind we also can study in the present day. So thank you very much, and I'm very happy to take some questions until I'm stopped. So, any questions? Yes. So the question is about warm-bloodedness and reduction of size. And I think the evidence we have from the bone histology is that all these dinosaurs were warm-blooded in some sense. We often mistakenly imagine that there's only one kind of warm-bloodedness, which is what we've got. But in fact, when you look at modern mammals, for example, you can see a gradation all the way down to really quite inefficient models of warm-bloodedness. So likely they would have continued warm-blooded, but we expect the small ones would have, for them, that would have been much more important, I expect. And good evidence for warm-bloodedness in dinosaurs is the fact that many of them have feathers, and we'll look at that in the next lecture. Any other questions? Yes? Well, that plot was shown against the present-day reference, but in order to determine it in the geological past, you have to draw a map according to the plate tectonic reconstruction, but using the sedimentary rocks that you find to define the coastline. And so it's relatively straightforward to distinguish marine rocks from terrestrial rocks, and to home in on the coastlines as they were at that time. So it comes from that kind of calculation. And typically people follow through thick piles of rock where they can track in a single space, marine to terrestrial, and you can see the sea retreating and advancing, for example, through the nature of the rocks. If they have marine fossils, if they show particular characteristics, you can determine that. Yes. It keeps changing. Oh, yeah, that's right. So it's only at an instant. So you follow through thick piles of rock. So much of that standard sea level curve, which was developed by Dr. Vail for Exxon Corporation, it was actually done in the south of England. This is a wonderfully long sequence of the whole of the Mesozoic. You can just follow through Triassic, Jurassic, Cretaceous. So at least for that location, you can see bed by bed, which is every 500,000 years, you can see exactly where the sea level is. But then you do that again and again in many different parts of the world. It's very complex, yes. Any other questions? Yes. Yes. Okay. So the question is, what was the fate of these dinosaurs and I guess dinosaurs in general? So in fact, Hatzeg is Maastrichtian in age. It's very close to the very end of the Cretaceous as it happens. And so I think the disappearance of these Romanian dinosaurs is a part of the disappearance of all dinosaurs. I don't think we're looking for a local theory just for these islands, because in fact the islands persisted and sea levels fell and they became connected. And so it's the question of the loss of all dinosaurs. And I think the model that most people find strongest is linking that extinction to the impact of the great meteorite, the Chicxulub crater in Mexico, and the consequential blacking out of the sun by the dust and debris that would be thrown out, the loss of light for photosynthesis, and the generation of a kind of nuclear winter. This whole work by Alvarez gave rise to all the thinking about nuclear winter, and then extinction following that. But as we discussed before, also we have to take into account the fact that the Deccan traps were erupting at that time, so there were large igneous province eruptions. So we have a vast challenge physically on the Earth happening at that time, with darkness and freezing perhaps caused by the meteorite, and other kinds of grim effects caused by the eruptions as well. So I think it's the global extinction of dinosaurs that also saw the end of the Hatzeg dinosaurs as well. Oh, yeah. So the question is about polar ice caps and whether they sit over the sea or over a continental mass. My understanding, and this isn't my field, but my understanding is that when there is a continental mass underneath, the ice cap will get bigger, and this is because of the albedo effect, which I'm sure is in your mind. So my understanding is that, and certainly at the Permian glaciation, that happened over southern Africa and parts of Gondwana more widely, so that enabled it to grow larger. And the albedo effect, which I'm sure people are familiar with, is that as an ice cap grows in the winter, and it may disappear in the summer, and that's the beginning of an ice cap, but the ice itself will form a white mass which reflects the sun, and therefore that slows the melting. And so that maintains the ice cap for longer, and that can encourage growth. And if it's on land, it's easier to grow because there's no convection of warmth from the seawater coming up from underneath. Any other questions? I see. Yeah. Oh, sorry. Yeah. Oh, last question. Thank you. Yes. Yes. The dwarf. Yes. Yes. Yeah, this is a fascinating question, because this whole question of dwarf animals on islands may affect human beings. And some of you may recall, I think you're right, maybe 5 or 6 years ago, Flores man was found on one of the Indonesian islands, was announced in Nature as a new species, Homo floresiensis, but then critics came back immediately and just said, oh, these are microcephalic dwarfs, meaning they're normal Homo sapiens, but just happen to be diseased or small or something. The counter-argument then, I think, was it's hard to imagine how you would have a whole population of diseased individuals and no normal individuals, let's say. One shouldn't use the word normal, perhaps. And so I think most people accept that these are island dwarfs because they were living on the island. I can't remember the height. They're about 1 meter tall, and otherwise they're adults. And for the same, using the same methods I was using with the dinosaurs, they can show they're adults. It's not a Lord of the Flies colony of little boys that have been somehow preserved. So there we are. This can affect humans as well, I think. The difficulty, I think, my final comment before I run off or I'm removed is that I think the difficulty people have in studying the Flores persons, are that the bones are in museums in Java or Indonesia, and it's rather hard for people to get access. And so it's been a little, I think the research has kind of fizzled down a bit because people can't get at them, and therefore it's difficult to make some new observations. But I better stop there. So thank you very much for your attention.